Previously, in dilations, we had been talking about the two things that control a dilation, which were the center dilation, which we're thinking of sort of like a light source that we're beaming. We're beaming some light through our shape, and it's the point that we're doing all our dilations away from. And then we have a scale factor, which we defined as a ratio of a new side length to an original side length, something on the image compared to a corresponding side length in the pre-image. So let me talk about that in just a little bit more detail here. So what this one is saying specifically is, let's say that I have this length here, which I will call AB on this pre-image. And let's say it's 3, right? And let's say our K, our scale factor, is just 2. Well, then how big is A prime? Whoops. A prime, B prime. Well, it should be twice as big. That's exactly what a scale factor of 2 means. So 3 times 2, it's 6. And now the definition of a scale factor here as a new side over an original side, you can see that I would take the new side of 6 and divide it by the original side of 3, and I could get that scale factor of 2 for sure. All right, now before we started talking about side lengths as far as the scale factor goes, we actually talked about the distance away from the center of dilation, which I'll call O, right? And this is going to help us in this next investigation that we're going to do in this video. If I were to measure the distance from O to A right here, this distance, and let's say it's 4, and my scale factor here is 2, then that means that O to A prime has to be 2 times 4. It's got to be 8. It's twice as far away from that center dilation as our original set of points. And again, if I were to divide them, 8 divided by 4, I get my scale factor of 2, assuming that that's what it is. Okay? Notice that those distances play out along the same exact ray that connects any two corresponding points. All right, let's go back to the slideshow and see what this investigation is all about. So in this investigation, we're going to do this on the coordinate plane, same kind of thing that we did on GeoGebra, except we're going to be drawing some things. So if you could please take out a straight edge and a compass. Now I suggested earlier in the first video that on my website that you should print out, whenever it loads here, you should print out the dilations handout. And on that dilations handout, you see that top graph grid that's right there. That's the one that we're going to work on right here in this investigation. If you don't have that, if you don't have capabilities of printing something out, then just take out a piece of graph paper that we can graph this stuff on. Okay. So step 1, I would like for you to construct triangle ABC on your coordinate plane that has these coordinates. A is at 3, 6, B is at 7, 6, and C is at 7, 3. So pause the video as you need to in order to actually do your little construction, and then you can come back here for further instructions. Okay, so I'm going to assume that you have graphed your triangle ABC, and it should look sort of like this, right? It looks like it's a right triangle. And I also have this point O marked here, O for the origin, and it's also going to be our center of dilation. Since it's our center of dilation, we're going to connect that point O to each of our points, each of our vertices in our triangle, with some light rays. So that's going to be step 2. So draw rays using your straight edge from point O to each of the vertices A, B, and C of your triangle. I tend to make them dashed because I think it looks a little cooler. Also, it's not part of the actual drawing, so it's a little easier to distinguish the dashed rays from the actual sides of our polygon, our triangle here. Okay, so pause as you need to so you can get that done. All right, so I'm going to assume that you have your little light rays, your rays that extend from O to A to B and to C. Okay, so now we're going to do that whole scale factor thing. We're going to find all of the points along each one of these light rays that are 3 times the distance away from point O. The way we're going to do that is with our compass. Okay, so this next step, step 3, it says take your compass and you're going to measure the distance from O to A. What that means is that you're going to put the point of your compass on O and put your pencil on A. That's how big O to A is. And then you're going to transfer that distance 2 more times along that same exact ray so that you find A prime that is 3 times as far away as the distance from O to A. So let me show you what the heck that looks like. So again, I'm going to stretch my compass from O to A. Put the point on O, put the pencil on A, and I'm going to make a little mark. That's how big it is from O to A. Now I'm going to take that same exact compass setting and I'm going to transfer it 2 more times along that same exact light ray. The second time I'm going to put the point of my compass on A, and the pencil is going to make another mark on that same ray. And then do it 1 more time, and that third point there is going to be A prime. If you were to measure the distance from O to A and get a number, and measure the distance from O to A prime and get that number, that new number from O to A prime should be exactly 3 times as far away as it is from O to B. So pause as you need to in order to catch up. All right, if you have that done, I want you to repeat that same exact process from O to B. So you're going to measure the distance from O to B with your compass, the point on O, the pencil on B, and then transfer that 2 more times along the ray from O to B. So pause right here to get that done. And then when you're done, it should look sort of like this. Here's my distance, and I copied it 2 more times along that same exact light ray. And now you've got 1 more to do. So take your compass, measure the distance from O to C, transfer that distance 2 more times along that light ray, so we get point C prime. That's 3 times as far away from O as it is to C. All right, and then when we are done, that's the location of where C prime should be. And then, of course, you want to connect each one of your points. And we have just dilated our triangle by a scale factor of 3. And I've dilated, I know, by a scale factor of 3 because all of my new points, A prime, B prime, C prime, are 3 times as far away from the origin as A, B, and C. All right, so far so good. All right, the next part of this investigation has to do with the coordinates, okay? So what are the lengths of AB and A prime, B prime? So let's go ahead and measure each one of those lengths. Come over here to G. I was about to say GeoGebra. That's not right, though. Okay. Let me scroll to catch up where you guys are. I think it's this one. Yeah. All right. This is fine. Let's find the length of A to B. So we're finding the length of this segment here. And to do that, just notice what these x coordinates are. If I follow this down, that one looks like a 3, and this one looks like it's a 7. So 7 minus 3, that should be a 4. So that one's 4. Let's do the same thing with A prime to B prime. So following this thing straight down, looks like it hits at 9, and this one hits at 21. So 21 minus 9. 21 minus 9 should be 12. Okay. Whoa, hey, where'd it go? So there's the corresponding side length there. All right, and notice that the scale factor still comes into play. That 4 times 3 is 12, and that side length from A prime to B prime is 3 times as big. Let's try that on another segment, shall we? How about B to C? So from B to C, I do believe that this one hits at 3 and at 6, so this one is 3. How big should B prime C prime be? Well, 3 times 3 is 9. This segment should be 9. Let's see if we can verify that. I'm calling this straight across. That one looks like it hits at 9, and this one at 18, and that is in fact 9 for its corresponding side length. All right, so we can see that that plays out as far as scale factor goes, side lengths, and the distance away from the center of dilation. Both of those things are true. All right, and then now let's take a look at the coordinates of A prime, B prime, C prime, and compare those to the original coordinates. So let's do that too. All right, let me clean this up just a little bit because there's too many lines in here. There's too many. And I erased those lines when I probably actually needed them so I could see what the coordinates of each of these points were. All right, anyway, so let's take the coordinates for point A. Point A looks like it's at 3, 6. And let's look at the coordinates for point A prime. A prime looks like it is at 9, 18. So compare those two. All right, let's do another set of coordinates here. Let's look at point C. C's at 7, comma 3, and its corresponding point at C prime is 21, comma 9, 9. Take a look at those coordinates. Compare those. Now, I understand whenever you're doing this on your own, yours might be off by a smidge, and the reason why it might be off by a smidge is that whenever you went to line up these 2 points and kept going with your straight edge to make that ray, you might have been off by just a little bit. Further away you get from that center point, of course, the more and more error you're going to have. All right, now one more set of coordinates. Let's measure those things as well. We've got B at 7, comma 6. So if we try to make a conjecture here, looking at each one of these coordinates, 3, 6, it goes to 9, 18. 7, 3 goes to 21, 9. Doesn't it look like those coordinates are 3 times as big? Hey, Rowan, why don't you go ahead and say hi?
Hi.
He snuck in and gave me a hug. He's so cute. All right, and so if that's true, what should the coordinates be for point B prime? Let's just multiply them by 3 and see. So 3 times 7 is 21. And 6 times 3 is 18. Does that set of coordinates make sense for that particular point? It looks like it's holding true. All right, so that these two things, it looks like the scale factor also affects the location of each one of the coordinates. So, man, if that's true, it really would simplify the process of doing a dilation. I wouldn't have to bust out my compass and straight edge each time. All I'd have to do is multiply the coordinates. But there's more to it than that. There's definitely more to it than that, as we're going to see in the next video, where we're going to take this same exact investigation, we're going to bring it into GeoGebra and see what exactly happens to any point x, y under a dilation that's centered at the origin with a scale factor of k. Well, that's exactly what happened in the previous one, but that was just one example. So we're going to do this dynamically in GeoGebra, look at a whole bunch of different examples and see if we can generalize it.